Hi everyone, I'm Tom, and I'm going to be talking about distributed version control, games, and Git. So, what are the goals of this talk? So we're going to cover, just a quick overview of what kind of, basically by the end of this, you should have an understanding and hopefully ready to do of what problems version control systems try to solve. And then we'll quickly just do a quick overview of what Perforce is, how it works, and what its benefits are and why we use it. And then I'm going to go in. We're going to do the same thing for Git, but with the assumption that that you haven't used Git before, because Perforce is very common in the games industry. It's part of our job. Hopefully you will know what it is by now. Not going to make that assumption with Git. But then we're going to go into the trade-offs that each model makes, and then finally trying to begin answering the question is, would we ever want to use Git for games? So the content's going to be formatted in that we're just going to go quick overview of Perforce first, or Helix specifically, which is the name of the software, despite the fact that no one calls it that. Then quick overview of Git. Then we're going to quickly go into something called Git LFS, which we'll come to later. And then finally, we'll do Q&A and discussion at the end. What is Perforce? So Perforce is a centralized version control system. So what this means is that you have a server somewhere, it keeps track of project history, and in order to make modifications, you have to check files out, so you have to let it know which files you are going to modify. These file modifications are grouped into change lists. If no one else has edited those files, you can then check them in, so they get added to this global history, which is stored on a centralized server. And the centralized server keeps revisions of every file in terms of these change list changes. And the things with asterisks here are just things which are very Perforce specific and not necessarily, and doesn't necessarily apply to every centralized version control system. So the consequences of Perforce model is that project history is tracked in one place. So this is, this has got ups and downs, right? If you look at the project history, that is the history for the project for everyone. The central system knows who's working on which file. This can be especially good if you have files which are unmergeable, because you can make sure that multiple people don't try to edit the same file at the same time if you don't want that. But again, this is like, not all centralized version control systems work this way. Another consequence of this model, though, is that software really needs Perforce integration in order to be useful, because it's a complete pain to have to manually check a file out in Perforce and edit it in another program. So there's, if you're going to be using game engines or IDEs, they need to know how to check Perforce files out themselves. Otherwise, productivity can grind to a halt. Also, you can't work when offline. Or if you do work offline, because you can manually make files writable, then all the other benefits of things that you get from a centralized system like this go away, and then you have to manually, at the end, reconcile your offline work, let the server know what you have changed, and that can be a slow and laborious process as well. And finally, branches are more expensive, quite expensive, because you can create streams. So if, let's say, you want two versions of a project, and one has, is a slightly different version for with an experimental feature, or you have a release candidate and you have, a development stream, you can do that, but it's globally visible, and the decision to make a branch or a stream isn't something you do lightly. And that again has, consequences. So now we're going to quickly go into a brief explanation of what Git is. So Git is, they describe it as a source control management system as opposed to a version control system. And that's very important because Git is very much designed to work with source code in mind. When Linus Torvalds designed it, he focused on the problem of how do I manage my source code, because that is what he cared about, because that is what the Linux kernel is. And he made it because he couldn't find an existing version control system that was distributed, and we will go into what that means in a bit. Performant, because he thinks version control systems should be really fast, and secure, and we'll go into what he meant by security as well. We'll just go into how it works. So if you imagine a centralized VCS, right, this is how you imagine version control works, right? Is that you have, each computer has its own workspace where people are doing their work, and then when they've made some changes, they just let the centralized server know about it, and that keeps track of your history. And that is a fairly intuitive model, but it comes from the perspective of how do we share our work first, and then how do we version those changes second? Whereas Git comes more from the perspective of how do I version my work first, and then how does that work get shared second, which leads to a very different workflow. So a distributed version control system looks a bit more like this. So instead of having a repository or depot on a server somewhere, and everyone checking files out of that to work on, and then checking them back in a distributed version control system, everyone has the entire repository or an entire repository, and you can share them, and you can share changes with each other, horizontally. And if you want to, you can also optionally set up servers to be repositories as well, and then people can send their changes to that server and also grab changes back from them. And that can be a way to more easily share the changes you have. But the important thing is everyone has an entire repository, which is a very different model from centralized VCS. And I think you can begin to imagine what the benefits there might be, but also why maybe in games that can potentially lead to some very horrible things. So to build up Git, imagine that you just cared about modeling, versioning your code locally. So you're working on a personal project, it's just for you, and you want to be able to constantly make changes to your code and be secure that you're not going to lose those changes, right? So what would that look like? Well, you'd have your workspace, right, which would just be the files in the project in their latest versions, as they are. And then somewhere you'll have a database on your file system, which will just, through some kind of data structure, manage versions of those changes. And you can, and when you reach a point where you're happy with things, you can then tell that version database, take a snapshot of my workspace as it is right now and save it. And that's exactly how Git works. But the other thing that Git does is it makes sure, it guarantees that once you've saved a snapshot, it can't be corrupted. And that's very different from a lot of version control systems. So how does it do that? So in order to guarantee this level of security, everything is hashed. So what happens when you take a snapshot of your workspace and tell Git, take a snapshot of this and save it for me, what it does is it looks at your workspace and it hashes everything in it. So every file gets hashed, and then every folder gets saved as a list of those file hashes, and then that entire thing gets hashed itself. And basically this happens recursively until at the end you have a hash of the entire workspace. And then when you make a commit, all a commit is it's a file with a commit message, some other metadata, and then a hash, and that hash is just the hash representing the index of your root of the workspace as it was, and then also it finally has a hash which is the hash of the previous commit, and then that entire thing is hashed, and that hash is the ID of your commit. So this might sound a bit confusing, so don't worry, here's a diagram. So basically as you can see, for example, let's say you had a workspace and in it you had test.txt. So if, let's say, you were to make your first commit, what would happen is that you have the root of your work. If that file's in the root of your workspace, you just have a thing called tree, and that's just contains a reference to test.txt, and then that contains a reference to the hash of the entire file contents. And then your commit, your very first commit, is just a reference to the tree in that state. And then when you, let's say you were to make another commit, and in that commit you modified test.txt, and you added a new file, then what happens is that your tree then becomes a new file, and that file just has the names. So tree represents the root folder, and that is stored in the database as a file which contains the names of the files that were in the folder. And then each one of those names then has a hash next to it, which is an index to the contents as they were at that point in time. And then you just basically get this fairly simple data structure, but potentially can take a while to get your head around. So does that make sense, or would you like me to go through it again?
I don't get what the top one is.
This one.
Back.
Oh, so I think, yeah, what is that?
What is the first one?
I think what happened, so what happened there is that in that commit, a folder was added in the root of the workspace, and it contained a single file called test.txt, and the contents of that file were this. So what this is trying to demonstrate, right? So if, let's say, in your first commit, you have a file and it's got some stuff in it, okay? And then you delete that file, and then the project continues development, and then at some point, even if just by sheer coincidence, another file ends up in the project with exactly the same contents as another file did many, many commits ago. Because Git already has, because every repository contains the history of every single change ever made in it, right? If in version commit number 1, you committed a file with some contents, that got deleted, and then in commit 100, you then just happen to add a file with the same content. Because of the way Git works, it won't make a copy of that file. It will go, oh, I know I've already got a file with those same contents, even though it's from 100 versions ago, so I'll just make a pointer to those existing content. So it's like a very efficient space-saving mechanism. Does that make sense? So if you have a Git repository, for example, and it's got 1 billion files, but they all have exactly the same content, then because those files are indexed by their own hash, Git automatically will just store a single copy of that file and then just index it 100 times in all the different places it's copied. Does that make sense?
Yeah.
Cool. Good one. That was a good question. But yeah, so that's what's going on there. And then a commit. So a commit literally is just a hash as an index, and somewhere you will have a file with the hash being its file name, and in that it will contain all the metadata needed to find the state of the workspace at the point the commit happened. And this has some really interesting consequences. So how does branching work? So all a branch is in Git is it's a file with a name, and that name is the name of the branch. And then all that file contains is a hash, and that hash is just the index of the latest commit on that branch. And that's all a branch is. So if you were, let's say, to make a new branch called testing, all that happens when you say git make a new branch called testing, and let's say you were here, all it would do is make a new file, and that file just contains 120 bytes, which is the size of the hash, and those 120 bytes just refer to this value here. And then if you were to like add a new commit to that branch, what happens under the hood is that Git adds a new commit, then it just updates that file to point to that new commit. So making a branch is super easy because you just type in git make branch, give it the name of the branch, and all it does is make a 120 byte file, and it's super simple. I think it's 120 bytes. I could be wrong on that one. But just for comparison, I've made some notes on what I went through to make a stream in Perforce recently, but I'll go through that at the end based on time. But it makes for an interesting comparison. Merging. Branching being cheap is all good, but one of the things that's worth pointing out with version control is branching doesn't really matter that much. Branching being cheap is what you want, but the real thing, the hard problem that we care about, right, is merging. And one of the reasons Git has become so popular is because it's quite good at that, even though it uses a fairly simple algorithm. So the way Git merges stuff is, if let's say you want to merge, one branch into another. So let's say in this case you were in the master branch and you wanted to merge the testing branch into it. All Git does is it finds the most recent common ancestor of both those branches, and then takes that as like, this is when the branches were both the same. Makes a lot of sense. Then it just gets all the differences that have been made since that single common ancestor, and then does a three-way merge. So what it does is it looks at all the changes. If a change has been made in one place and the other branch hasn't touched that part of a file at all that's been changed, it's fine, it just automatically merges it. If both branches have had the same change made, that's fine, it just automatically merges it. And then only if two changes have been made which actually conflict does it say, you need to resolve this manually. And this works really well, and the amount of times you actually have to resolve merge conflicts is quite rare. And yeah, it's like, if you were to use Git full time in a job, like you would probably be merging 4 or 5 times a day, because every time you grab from the central repo, that's a merge. Everything in Git is done through merges because of the distributed nature. Everyone is working on their own branch all the time. So Git being good at merging it has to be. So how is this all implemented? Basically, in your workspace, there will be a folder called .git, and that's the entire repository. It's super simple. And then all of this stuff I just mentioned is just a content addressable file system stored in that folder. So you just have one folder which just contains the actual contents of all the objects that you've ever added to your repository over time, and those are just indexed by their hash. Then you'll have another folder which will just be all your branches. So that will just be a bunch of files with different names, and each one of those files just contain a hash. And then some other bits and pieces that you need, like for commit history and that kind of stuff. But it's super, super simple. And you can actually open that folder and see that, and it's very easy to actually introspect what's going on there. So finally, collaboration. So we've already covered how to merge branches locally. Collaborating is basically exactly the same thing, works exactly the same way. All you need to do is you need to be able to grab someone else's branch that you want to merge into your branch. So you just copy that to your machine, and you just do a merge. And it's that simple. And most of the time when you merge, you don't have to do anything. You very rarely have to resolve any conflicts. And even if you do, it tends to be quite good at letting you know what's actually gone on. But obviously, if you're working in a team, right, you don't really tend to have a flat, you don't really want like a flat structure necessarily where everyone is just horizontally grabbing branches from each other and sharing things that way. You ideally, most of the time, you really do want a central place that everyone agrees is the state of the project, that development is done on, similar to how with Perforce, right, you have a centralized place where everything is stored. And Git can very easily handle that because all you do is you have a Git repo just on a server somewhere, and there's nothing special about it except for the fact that we just agree that is the repo that we agree is the repo that is the source of truth. And then if you want to grab changes other people have made and added to it, you just do pull. So all you do is you just grab the branches and then merge them into yours, and that's called pulling. And then you can apply your changes onto its branches by pushing. And all that does is it basically does a merge. So it will copy your stuff and then merge it into the server. And in order to make sure that it can always do that, you just have to make sure that when you push, your branch is at least as up to date as its branch, because you can't really, the idea of handling a merge conflict as you push doesn't really make sense. But that is quite easily resolved by you just pull, then your version history is at least as up to date as the server's one. Then when you push, all it does is it just takes all the changes you've made since its latest version and just plonks them on top. So that's quite cool. So what a remote is it's basically just a URI or a URL. So just, like an IP address and then a folder name, which points to that repository. And then you can give it a name locally. And then Git just provides some syntactic sugar and helper commands to let you push stuff to it and pull stuff from it. And if, let's say, you initialize your repository by cloning it, and all a clone is you saying, I want to grab the contents of this repository from this server, what Git will do even also helpfully is when it copies that repository to your machine, it will set up a remote in your repository, and that's just called origin. There's nothing special about the name origin. It's just a name that's the default name for a repository you've cloned, and that will point to that server. So that's why, if you've ever used Git before and you've cloned a repository, you can immediately just, make a commit and then type git push, origin master, and it will know, oh, origin is the thing that I cloned before for this person, master's the master branch of this repository, and I'm just going to push my changes to it. Does that all make sense? Cool. Finally, so this is just a simple diagram showing how merging from a remote works. So it works exactly the same way as it does for merging any other branch. So if, let's say, you have your repository here, and it's got a reference to remote in it, which is this repository here, then what you can do is you can just say fetch this remote, so git fetch origin, and then it will copy it will go, oh, this person, we both have this commit, so I'm just going to copy these new commits that have been made since then that the user here doesn't have, and I'll put them here. Then if you want to merge the remote's changes into your branch, you just say git merge origin/master, and then it will just do a normal merge from this branch into this branch. So when you do a git fetch, all that basically does is it basically says, make a copy of the branch that the server has with this name and just copy it to my machine. And that will just be, and that's what that origin/master there is. Cool. So although we've talked a lot about the data structures that Git uses behind the scene, it's also important to just quickly cover the workflow. So for example, in Perforce, right, you have files you checked out, you can move them into change lists. So, you can say these are when I commit this change list, I want these files to be put in the change list, and then you have shelves. So Git has, different concepts. So you have the working directory. So this is just the state of, your working directory as it is. And Git automatically just keeps track of which files you've changed. So you don't have to check out files or let Git know in any way that you've modified it. If you modify a file, Git will just know, oh, that file has been modified. So then, there are commands you can use to ask Git, hey, which files have I modified? And Git will go, these are the files you modified. But then before you commit them, you have to stage them first. So this is basically telling Git, I know I've changed this file, and I want these changes to be committed in the next commit that I make. And then when you stage a file, it gets added to this thing called the staging area. And what's important to know is that if, let's say, you have a file called food.txt, you make some changes to it, and then you say to Git, I want to stage this file for the next commit I make. When you stage that file, Git will copy that file as it is and add it to the staging area. But then if you were to like modify that file again and you wanted to actually add those modifications to the next commit instead of the state it was before, you just need to tell Git again, restage this file. And that has some interesting properties. But one of the nice things about it is if you've made some change to a file and you know that that is the file in that state is what you want to commit, then once you've indexed it, you're quite secure in the knowledge that it will be committed how you want it to be committed. So if you accidentally then accidentally try to tab through like your browser, and while you're tabbing through, you accidentally open the IDE and like spam a bunch of keys without realizing it, and then actually tab through successfully, and then eventually go to push in, then you realize you've broken your file and everything's gone wrong. That won't happen because when you index, you can make sure the file is in the state you want it to be. And once it's indexed, it's safe, basically. And then if you accidentally make a change to it, then those changes won't be committed. It will be committed at the point it was when it indexed. Does that make sense? Because that can be a bit of a point of confusion sometimes if you haven't used Git before. But yeah, once you're happy with everything that you've staged, you can write a command to say, hey Git, what are the changes I've made and what are they in the index? You can look through those. Then once you're happy, you can just commit them. And then it does all the hashing magic, and now you've made a commit. So obviously, I've covered the data structures in depth and that kind of stuff. And I think it's an important thing to cover because I think once you understand that, it makes using Git a lot easier because it has a lot of oddities to it, which make a lot more sense when you understand what it's trying to do. But obviously, I haven't covered like how to actually use Git. And the reason for that is because there are many different ways to do it. There are, graphical user interfaces you could use. Many applications have their own Git integrations, and they can all work in slightly different ways, but fundamentally they're all doing the same thing. But what I've done is I've added some references resources at the end of the slide deck, and I'd recommend checking those out. The Git book is really good. So on the official Git website, there's a book that explains this stuff really well. Another thing I'd recommend, which is outside of how to use the software, but important if you want to use it effectively, writing good commit messages is like a really useful thing because it can be really useful, to trace through history if you ever need to solve a difficult problem and work out, oh, this is why this thing was made. And it's so important that Linus Torvalds describes his job now as just making sure. So when he doesn't code anymore, he just maintains the Linux kernel. And the way he does that is someone will say, can you, grab my changes that I've made to my branch. Then he'll look through the Git commit messages, decide whether or not they are, A, if the changes are good enough or not, but then B, he'll go, are the Git commit messages good enough or not? And he considers that the more valuable part of the work he does, and then he'll merge it in. So good commit messages can be really good. And then obviously there's those tutorials in the resources link as well. So let's talk trade-offs. So one of the things that's worth pointing out with performance, and this is the point that Linus made when he was, explaining Git at a talk he gave, is that performance is not necessarily, or isn't doing the same thing but faster. But when an operation becomes much less costly than it would have been otherwise, if like branching and merging is a lot cheaper than it would be in another system, you don't end up doing the same things you would have done before but faster. You end up completely changing your workflow. And that's an important point to stress when it comes to Git, and especially when it comes to branching. And I know from experience that when using any centralized version control system, you really try your best to avoid having to make a branch or stream unless it's absolutely necessary. Because they're globally visible, and having a really complicated stream graph in Perforce can be really annoying to navigate. But also just merging is a pain. And again, I'll go through at the very end, I'll go through the many-step process I went through yesterday to set up a new stream. And even though it's something I'd done many times before, I still made mistakes. And yeah, but it's a bit of a rant, so we'll get to it later if you've got time. But it's worth pointing out, yeah, so cheap and fast branches completely change the way you use version control. Like you can very easily make multiple branches a day, just do some quick experimentation. And even if your code like isn't in a working state, but you've made a change you want to be able to roll back to, making a commit is something you can do instinctively because you're not going to affect anyone else. It's just on your machine. And that's really powerful, especially when it comes to code. So yeah, and also once you start branching and merging more often, then the merge themselves become a lot easier because they're going to be a lot smaller in like the changes that are made. If you're constantly merging, then the size of each merge is going to be comparatively small. So when there is like a conflict there, it's very easy to resolve, or much easier to resolve than it would have been otherwise. And also when you do a merge, and if let's say you mess up the merge, it's very easy just to roll back to where you were because you can only merge two branches once they exist. And if two branches exist, it means they're already hashed, they're already in the repository database. There's no way of losing that data unless you really, really want to, like deliberately delete it. But just don't do that. Git lets you do everything, but if you stick to like the safe commands, you're not going to do that. So you're much less likely to like accidentally delete your work or stomp it, or have like some files. One of the things I've done often in Perforce is I've done a merge badly, and then because I wasn't thinking straight, I like instinctively hit revert, thinking I'm going to revert this merge and go back to where I was, and it doesn't do that. It just reverts everything, and now you've lost all the changes you've made, and that can be really frustrating as well. With Git, you have that security, right? Even if you accidentally like completely delete all the merging you've done already, you're not going to delete the changes you've actually already made and committed, and that's really important. Git is awesome, right? You've got, it solves a lot of problems, fixes a lot of issues that you might have had with Perforce in the past, but unfortunately, it's not so great when it comes to binary files. So the problem with binary files is that they're really hard to diff, which means it's very hard to with text files, it's very easy just to take the delta of changes that happened over time and store only those, which can make storing the history of a text file very, very cheap, and text files themselves are already quite small. Whereas binary files tend to be much bigger and you can't diff them. So each version of the binary file is just a copy of the binary file with the changes made. And then also with a binary file, every client has the entire history of the entire repository, which means that, if you have a 5 GB binary, if you have 5 GB file, for example, not that you'd have one that big, but and it's been modified 5 times, then you're going to have 25 gigs of data on everyone's machine already, which is incredibly expensive. And because everything's so distributed, you've got no way of letting other people know that maybe you're modifying a file and that they should hold off on modifying it themselves, because it's going to be a pain to merge. And so yeah, good luck merging them. There's no magic algorithm for merging binary files. So that can be a huge pain as well. But the benefits of using Git with source code are big enough, and it's gained enough traction that people have started investigating potentially using Git in an environment where it could work a bit more nicely with binary files. And one of the more popular systems is this thing called Git LFS. And all this is a wrapper around Git. And what it basically does is when you commit your code and check it in, instead of checking the file as it is into the repository, what it will do is it will take that file, store it on a file storage somewhere else, and then what's checked into your repository is a tag file, which then lets Git know where on the large file storage, or Git LFS know where on the large file storage that file is located, which means that your Git repository now just contains the source code and then loads of tiny tag files which point to the actual binary data. And this has some interesting consequences, right? So it's not too difficult to use. because when you check files out or check branches out, it uses various hooks and filters to automatically replace those tags with the actual file contents for you. And then when you commit, it does the inverse. It replace those files with the little tag files, and then we'll make sure they get put on the large file storage. But this has some consequences, right? So binary data basically has all the positives and negatives of centralized VCS, because that's what they basically now live in. They live in a centralized VCS system. And code has many of the benefits of distributed version control. So as long as you're not changing binary files and only changing code files, and you've already got the latest binary files, you can make all your code changes you want. You can, branch. You can do merging really easily. There's also other things about Git in the way it works, which is unrelated to it being decentralized, but just due to the fact that it's not Perforce. So that is a nicer workflow, but it comes at the expense, of an extreme blow up in complexity of your version control system, right? Where, there's a lot of niceties to be had, but now the system's very complex, and one of the things that's important as well is that it's not just programmers working on a project; artists are working there on it as well. So that brings us to the question: is Git the future in games? And one of the reasons I decided to give this talk is because things do seem to be trending that way. Git LFS is slowly growing in popularity. Companies like Unity are, investigating, or there already do exist Git LFS plugins for Unity, which provide a nice UI for using Git LFS. So they seem to be heading that way. Unreal, if you want to grab the Unreal source code, it is a Git repository, and that's the way it works. So it is starting to sneak into things. Unity packages are developed using Git. So even though Perforce is likely to stick around for a while, there already is a transition period going on where, programmers will have to know how to use both, at least in the short term. And in the long term, things seem to be migrating to fully using this larger system. But the main challenges it faces are usability, scalability, like no one's proven if a workflow like this can work scalably, and then also maturity. Like Git LFS still has a lot of teething issues, like the fact that if you lock a file in Git LFS, that file is locked across all branches, which is kind of nuts.
It does make sense.
It does.
You cannot merge them.
It does.
If you lock on one branch, you cannot merge it.
That would make sense if it also wasn't for the fact that it does let you modify those files independently. It just doesn't let you lock them, which is really dumb. Yeah, you would ideally want to be able to say these files, like you would want to be able to say with some files, like no matter which branch this file is on, it can only be modified in one place. And then for some files, you might want to say, but at the moment, it just has this really weird system where it will let you lock a file in one branch, then no one else can edit it, and then unlock it. But then someone else can still edit it in another branch after that, and then you still have that merge conflict. So it's teething issues. So here's a list of recommended websites. So I'm going to send out an email with a link to these as well. The official Git website is where you can download Git from. The Git book is really good if you want to learn more about the internals especially. Really recommend this article on how to write a Git commit. There's also an intro to Git workshop I gave when I was at uni, which goes over like more of the basics of how to use the command line interface. There's a website called Learn Branching in Git, which has like a nice visualization where you like write Git commands and it visually shows you how your repository tree grows over time. Then there's a Git command cheat sheet, which is really good. Once you've learnt the basics, you can just have that open in a tab and refer how commands work. And then I've not used it myself, but Git Kraken's been recommended to me as a GUI around Git as well. I'd also just like to, thank Hugh for organising the reading group, as always, and also AJ for providing some valuable feedback on this. And then finally, any questions?